In this tutorial, we will introduce the ion implantation technique available in our laboratory and demonstrate their applications. The tandem accelerator supplied by the Dutch company High Voltage Engineering was installed in a new hall adjacent to the Van de Graaff accelerator facility in Res near Prague. The accelerator was put into operation in November 2005. In a tandem accelerator, negative ions are produced in a cesium sputter source or duoplasmatron, where sample atoms capture electrons after being ejected from a cathode. These ions are extracted by a potential, focused by electrostatic lenses, and passed through an analyzing magnet. Inside, the beam is attracted to a central positive terminal, where charge stripping converts the ions from negative to positive. Now positively charged, the ions are repelled by the terminal through the second stage, gaining further energy before an analyzing magnet, which selects the specific charge state and energy required for the experiment, ensuring a pure and precise ion beam. After the analyzing magnet, a neutral trap uses electromagnetic fields to deflect charged ions into the implantation line, while unsteerable neutral particles from charge exchange continue into a beam dump. This prevents compromised fluence accuracy, ensuring a pure beam for successful implantation. Ions penetrate the sample and lose their energy through two primary mechanisms: electronic interaction with the substrate's electrons and ballistic collisions with atomic nuclei. The ions eventually come to rest at a specific depth determined by their initial energy, the ion species, and the properties of the target material. Some ions penetrate deeper, while others stop closer to the surface. As a result, the implanted ions typically exhibit an approximately Gaussian depth distribution. When implantation is performed along major crystallographic axes, ions can enter channels, leading to uncontrolled penetration into the structure. Therefore, implantation is generally carried out at an angle to suppress channeling effects. Displaced atoms may occupy interstitial positions between lattice atoms, leaving behind a vacancy, Frenkel pair, or they may replace a lattice atom, resulting in a substitutional position. Similarly, implanted atoms can occupy either interstitial or substitutional sites. Atoms located in interstitial sites partially block the main channels, and the resulting damage can be analyzed by RBS in channeling mode. Monoenergetic implantation allows for material modification at a precise depth. This technique is applied, for instance, in the study of radiation damage in alloys and the doping of crystalline structures. In contrast, multi-energetic implantation is suitable when aiming for uniform irradiation of a specific region. Using combination of SRM and our in-house code, we can achieve an almost uniform ion distribution over a defined depth range, resulting in a box-type implantation profile. The main advantage is that ion implantation allows for very quick and easy modification of solid materials. It gives us the ability to precisely dope materials or create controlled defects in crystals, which is essential for tailoring their electrical, mechanical, or optical properties. However, there are certain limitations we must consider. There is always a risk of radiation-induced damage of the sample. For sensitive samples like polymers, we have to be very careful about the potential for thermal degradation during the process. In terms of specifications, our system can work with elements from hydrogen up to gold, excluding inert gases, lanthanides, and radioisotopes. We typically operate within an energy range of 0.6 to 30 MeV. Through the utilization of ion implantation in glass, crystals, polymers, or 2D materials, we have the capability to generate optical waveguides, introduce nanoparticles into the material, create nanostructures, or alter the surface of the sample. Such processes can result in the modification of electrical, structural, and optical properties. Thank you for your attention.